Okay, cool. Thanks so much for joining, everyone. I'm super excited for today's presentation. Today we have David Abel, who's a senior research scientist at DeepMind in the UK. He's based in Edinburgh, and before that he completed his PhD in computer science at Brown University. I've listened and attended a few talks that David has done, and he always gives like really amazing talks, and he's very kind to the readers. So I'm sure this is going to be a great talk. And he's going to speak about a little bit about continual learning and his, I guess, formulation of continual learning and what it means for agents to never stop learning, and some interesting little extra things that have been thrown in there. And I think this applies to a lot of people working in a lot of fields in RL, whether it's transfer or generalization or even continual learning. But yeah, really looking forward to this talk, and thanks, David, for joining us. I think I will hand over to you.
Amazing. Thank you so much, Caleb. Thanks for the invite and for the really kind introduction. Really appreciate it. Yeah, great to be here with you all. I'm going to speak about this work on defining continual learning. And I was telling Caleb before we were chatting, just that this is the kind of work that I think brings about a lot of opportunities for disagreement. So I would love to hear any kind of challenges, questions, concerns, spicy takes that people have along the way. So feel free to interrupt at any point with questions. So this project is joint with my collaborators here on the screen. So André, Ben, Doina, Hado, and Satinder. This was one of those projects where the six of us just could not kind of resist debating together about these topics for years, and resulted in the proposal that I'll give today. So huge thanks to my collaborators. It was a really fun group to work with. So the goal of this work is going to come up with a general, clean definition of the continual reinforcement learning problem. And so along the way, we'll have to both define what do we mean by the sort of standard reinforcement learning problem, and then how does this continual element make changes to that proposal. Those of you that saw my talk last week on the reward hypothesis will kind of see what's coming next, but I think it's worth maybe pausing to reflect on why we should care about definitions to begin with. It's kind of a weird object to focus on within science, just because oftentimes we're focused on, say, a hypothesis, on a method, on experiments. But I think definitions themselves are sort of useful objects to spend time to really make sure we get right as a community. There's this beautiful quote from this analytic philosopher, Willard Quine, who says, "The less a science is advanced, the more its terminology rests on an uncritical assumption of mutual understanding." So I love this quote, and this quote has really, I would say, inspired me to try to think more about definitions. So of course, within AI, we have this central concept of intelligence that the field sort of orbits around. And there've been some proposals for definitions within the field going back to, say, this 1956 Dartmouth workshop that really kicked off the field. But similarly, I would say we have debates around what exactly the definition of learning is or should be, and we'll see some of that play out in the talk today. But we even have definitions of, say, things like convergence that I think are quite contentious. It can be kind of hard to pin down what exactly we mean by these things. And we could, for instance, look to other foundations for definitions that we can kind of make use of in AI. So for instance, from other foundations of math, like set theory and arithmetic, we get concepts like true and false, what it means to negate something, what, say, a number is, this sort of thing. And from probability and the probability axioms, we get notions of maybe belief and knowledge, uncertainty. Computation, we get things like reasoning, and from maybe other nearby fields, we get other kind of grounded definitions of different concepts. But I think the central concepts of AI, things like agency, intelligence, and learning, don't really have a home with just one of these other areas. We can't really pin down maybe one set of these foundations that we can pull on in order to establish maybe a clear foundation for AI. Maybe, for example, you can connect, say, rationality from sort of classical decision theory, but I think there's reason to maybe depart from rationality alone. That is to say, it's not clear that the sort of classical notion of decision theory fully captures what we mean when we talk about things like agency, intelligence, or learning. So with that in mind, what this talk is going to be about is trying to, excuse me, come up with a get some water, hold on. All right, excuse me, thanks. Come up with a definition of learning. So at the center of this work is going to be a proposed definition of learning. Unlike maybe other artifacts that you might work toward in the sciences, it's maybe less clear what it looks like to have gotten the definition right. So we proposed 3 characteristics you might look for a suitable definition. I don't think those are the only 3. I think there's many more, in fact. But the 3 that we really focused on was one, what we call the yields fruits, which means that the definition can give rise to kind of interesting perspectives or insights or tools or something that maybe you couldn't get from just the definition itself. The second thing we looked for was a really minimal, clean, and precise formulation of the definition. So I want to emphasize that precise piece, because if you lose precision, then there's the opportunity for that ambiguity that Quine talked about kind of sneak into your definition. You can kind of escape the true complexity of the concept you're talking about if you're not precise about it. So the third characteristic we looked for was to capture our intuition, so our kind of collectively within the community. So we'll see whether that actually plays out with our definition. We'd like to capture known cases, so examples of, say, continual learning that people have been studying for quite some time. We'd hope that our definition can, in fact, kind of accommodate and agree with those cases. And this last one, the holds up under scrutiny, I think is, again, it's an ongoing process that will probably never end. You know, we as the 6 that were working on this tried our best to scrutinize the definition. We pitched it to some folks along the way as we were developing it. And a lot of the process was identifying holes or weaknesses in this definition, iterating on it, and then proposing a more refined version. And so I would say this, whether it holds up under scrutiny, is still kind of actively an ongoing process. So please feel free to scrutinize and poke holes as much as you can. Okay, so when we try to define something like continual learning, I think we can really study these 2 as constituent parts. So continual, I will claim that we roughly know what we mean when we talk about continual. It's just the kind of process that keeps on going. I will, however, claim that we don't really know what learning means, as I alluded to at the beginning. And so at the core of this project was an attempt to try to formalize what learning could mean. And this is, building on this long history of work across several different fields, control, psychology, cognitive science, and so on, that really try to pin down a precise definition of learning. And one little allegory we've reminded of a number of times throughout the project was this notion of these mystics inspecting an elephant from different angles. And one of the mystics, looks at the tusk of the elephant, the other looks at an ear, the other looks at the foot, and they each see different characteristics of the elephant. But just by looking at that individual characteristic, until you get that whole picture of what the elephant is, you don't really know that they're all in fact looking at the same thing. And so we think about different definitions of learning from, say, the perspective of, learning is something like a behavioral change, which is an often discussed definition in a lot of the psychology literature. Or perhaps you could talk about maybe a more machine learning focused definition of learning, where learning is when performance improves. Or perhaps more of a Bayesian notion of learning, where the uncertainty of a system decreases. Our suggestion is that these are each kind of angles on this elephant, and we haven't quite gotten the holistic picture just yet. And so along the way, as we're kind of unpacking this proposed definition, I think a question that's useful to have in mind is which of the properties of learning, so behavioral change, performance improvement, these kinds of things, are symptoms rather than sort of the true essence, which of them are the tusk rather than the elephant itself. And in our attempt to try to get to the bottom of this, we came across, we've proposed really this 4-pronged taxonomy to thinking about definitions of learning. So we suggest that most of the existing definitions fall into one of these 4 categories. The first I'll call the mechanistic approach to defining learning, which means that an organism or an agent learns when it makes use of some internal cognitive mechanism. So in, say, machine learning, maybe it's computing gradients, or maybe it's carrying out search of some kind. And maybe on the biological side, maybe there's some agreed upon thing that certain kinds of organisms have to do in order to be learning in some meaningful way. The second style of learning we'll call the behaviorist account, which means we only get to inspect the behavior of an organism or an agent to determine if it's learning. So here we might put a little hiker into different situations. Maybe we put it next to a bridge. Maybe we put it next to a waterfall, next to an unbuilt tent in a forest. And we inspect, can this agent do different things when subjected to these different experiences? And we would say this agent is learning when its behavior is indicating that it's able to respond to these different experiences of the relevant. The third approach is roughly the Bayesian view that says an agent learns when its uncertainty decreases. Maybe it's searching through a space of worlds and it's kind of slowly improving its knowledge of the world over time. The fourth, I would say, is the most canonical within machine learning. This really has a home in this Mitchell textbook on machine learning, where he roughly defines learning. An algorithm is learning when its performance goes up. So any method that's going to tether learning to some notion of performance will categorize in this performance-based view. And as I mentioned, each of these four have some kind of deep history in the literature, again, spanning things like machine learning, but also psychology and control. And maybe I'll just pause there, actually. Are there any questions or just reactions to these four before I move on? Okay, perfect. So with that, I will propose, I think there's a lot to say about this taxonomy, these four approaches. We are going to adopt this behaviorist view. I won't say too much more about this. I'll just briefly comment on one reason we didn't choose the others. So the mechanistic view, we view it as a downside that you have to commit to some particular inner mechanism of an agent or organism as being somehow special. And we at some point agreed that at the very least, we couldn't identify such an important mechanism, but maybe there's still such a mechanism out there. The uncertainty view, similarly, you have to commit to a choice of what uncertainty matters. So what is it that you're actually modeling as uncertain? What is the quantity of interest? So it's similar to this commitment about what mechanism matters, but what uncertainty matters. And the fourth view, this performance view, we felt that by adopting this view, you're really moving all of the interesting semantics about learning into things like performance or the objective, right? If we write down, we say an agent learns when its performance goes up, we've basically just said, well, the performance just is a measure of learning then on its own. So we haven't really decoupled these two concepts. That being said, I think each of these three are kind of worth more investigation on their own right. As I mentioned, we'll adopt the behaviorist view. This is really just because it resonates the most with the kind of implicit assumptions of RL. It treats the experience stream, like actions, observations, as sort of the fundamental quantity of interest. Okay, so now that we're going to adopt this behaviorist view, it's worth briefly commenting on the sort of standard view within reinforcement learning, which is, we think about, say, chess as an example, or some other board games. When we think about reinforcement learning algorithms and their success stories in the past, oftentimes what we find is that these algorithms play these games for some number of times until they eventually solve the game. So as an example, if we look at other standard benchmarks, things like Montezuma's Revenge from Atari or Mountain Car or StarCraft, there's almost an implicit notion that these agents are searching over some set of behaviors. So there's the set of policies that we care about that can move the little Montezuma's Revenge character through this maze, or manipulates pieces on the chessboard. And we might imagine that there's some kind of optimal solution out there somewhere, and we'd like this agent to find that optimal solution. So imagine maybe the agent is initialized as this green circle, and that through interaction with its environment, it's slowly switching its policies until eventually it finds this optimal policy, and then it can stop learning, right? So this is the policy that clears the breakout bricks as quickly as possible. It's the policy that moves the mountain car as quickly as possible to that flag at the top right, and so on. And so I think really what we're seeing is that there's this implicit view of traditional reinforcement learning to treat the learning process as solving a problem. That is, there is a specific, maybe finite or contained problem for this learning system to eventually solve. But in contrast, continual learning, we can think about as just endless adaptation. We can think about it as the case where there's no solution to be discovered, but we just want the agent to endlessly adapt to its experience. So if we think about this in terms of this set of representable behaviors, this would just mean that we're removing that single solution and instead just suggesting, gosh, this agent just needs to keep searching forever. It needs to keep adapting its behavior endlessly as it continues to interact with its environment. So that's really the distinction that we're going to try to formalize. On the left, agents that eventually stop their search and settle on one choice of a policy. And then on the right, what we'll call continual reinforcement learning, which is cases where the agents continue their search for a good policy forever. So the rest of the talk is how do we actually make that distinction nice and precise. And really, in order to do this, we're going to need some new mathematical language to talk about agents in a particular way. And those of you I just had lunch with the other day, was kind of rambling on about a call for agent emphasis. So I wanted to just mention that there's going to be this running theme throughout the talk today to give us maybe more language to think about and talk about agents as objects. So right, this is the one rendition of the classic RL diagram. And all of our models, or at least most of our models, tend to live on this top side. That is the model of the world. So the, of course, the MDP, it's one way of writing down the problem that the world presents to an agent. We have things like classes of problems, so maybe bandits, contextual bandits, MDPs, POMDPs, and so on. But if we draw this line that separates the world from the agent, I would claim we don't really have a standard kind of canonical model of what an agent is, nor do we have kind of standard definitions of classes of agents. So Rich Sutton wrote this beautiful paper at RLDM in last year or two on the search for the common model of the intelligent decision maker. It's a really nice paper, and it suggests that we should be looking for a kind of canonical model of what an agent is. And I really agree with this proposal, and I think we would benefit a lot as a community from having this extra modeling power to study agents in their own right, in addition to studying worlds and problems. Okay, so with that, I'm going to move on to some notation, but maybe I can just pause there again to check to make sure any questions or comments so far. Okay, perfect.
I'll ask
maybe there was one.
Question.
Yeah, sure, go for it.
Like, why do we want to do this? Why do we want this, I guess, agent-centered approach? Like, what are we losing right now in, I guess, the agent and MDP formulation that's quite common? Is it related to the continual learning, or would you say even outside of continual learning framing, this would be interesting?
Yeah, it's a great question. I do think we probably lose something. What exactly that is, I think it's a great question. I'll have to think about it more carefully. But maybe my immediate reaction is to say most of our almost universal results or sort of law-like proposals for things like reinforcement learning tend to be about either the environment or about the problem itself, so about MDPs. So MDPs have this particular structure or property. We have, of course, guarantees for certain algorithms, but I think what would be, to me, really powerful as a community is to come up with laws for agents that would go beyond any particular choice of environment or environment class, if the environment can be well represented as an MDP. If we can instead say something fundamental about what will make an agent reliable or robust, regardless of the environment that it interacts with, that's the kind of results I think I'd be really excited about. That I don't think we don't have the language for being able to formulate those results yet. But again, it's a great question, one I'll have to think about more.
Cool, thanks, makes sense.
Yeah, thanks, Caleb. Okay, so next, I'm just going to introduce some notation. So the reason I'm have a notation slide is that we're going to, as I mentioned, just introduce some slightly new twists on the typical way of writing down RL. So it will hopefully look familiar, but it just has some new ingredients to it. A lot of this is going to be inspired by this line of work on general RL from Marcus Hutter and colleagues' work, as well as some recent work from Ben Van Roy's group, led by Shidong. There's this beautiful paper, Simple Agent Complex Environment, that I got a lot of inspiration from in working on this project. So we start from what we call an interface, which is just a set of actions A and a set of observations O. So this is the contract of what information the agent can exchange with the environment. That will give us the set of histories, which are just these little objects H that are just the sequences of pairs of actions and observations. So of arbitrary length. So it could be empty, it could be length 10, it could be infinite. So in general, we'll talk about cal H as the set of all histories. So this is the set of possible interactions that could occur between an agent and environment that share an interface. The environment is then this function E that maps any history and then the agent's latest action to a distribution over observations. And the agent is a function lambda that maps the history to a distribution over actions. So this is just a history-based policy. That's our treatment of what an agent is in this case. We remember we adopt that the behaviorist view, which will mean that all we care about in terms of an agent is how it translates experience into action. When we talk about performance, we'll just use a function v that's a function of an agent and an environment. We'll occasionally talk about the value or performance conditioned on a history. And at some point, we'll basically replace this with something like average reward or traditional kind of expected return. But for now, we can kind of abstract and just think about this notion of v. But I really want to talk more about this agent object. We're going to need, as I mentioned, some new language to talk about agents. And that's really where a lot of the main focus of the work is. So we think about an agent as belonging to some set, Blackboard lambda. This is the set of all agents. So once we fix an interface, this Blackboard lambda is the set of every possible history-based policy over that action and observation space. And then we'll use big lambda to refer to any non-empty set of agents. So it's basically a set of history-based policies. We'll just be calling them agents. So I would say that's going to be the most important notation from this work. It's this big lambda set of agents. Blackboard lambda is the set of all agents. Okay, so I'll say a tiny bit more about histories because we'll need this just for some of the nitty-gritty pieces. Oh yeah, was there a question?
Yeah, just maybe a small one. Maybe I missed it, but sometimes agents are just maybe written like with an I. Why it's now a lambda? Or what? I read a lot that I don't know. See it quite often that we call the agents like with the iteration of I, and it's until n number of agents. Is this now like a different type of agent, you would say, and therefore you call it lambda, or why did you change it, or I just have a wrong impression of that?
Yeah, that's a good question. So there is definitely a lot to be said about kind of making sure the notation is appropriate, chosen in the right way. The other notation we considered was pi. I think maybe, so one piece I should emphasize is all of this is going to be single agent RL. So we will only ever be talking about the problem facing an individual agent. And so because of that, we won't be indexing into different agents at the moment as teammates or collaborators or anything like that. But I think in doing that, I would definitely want to make sure we're adopting the conventions of multi-agent RL in the right way. I can maybe comment on why we didn't pick pi, which is what I guess I tend to see for these history-based policies in other literature, which is that we really wanted to emphasize the point that an agent and a policy are effectively the same object. The difference with policies, we maybe tend to think about them as belonging to this special class of stationary policies that only react to the latest experience. Whereas the agent, so say in Q-learning, its policy is this argmax over the Q function, but the algorithm of Q-learning, we don't write down in some abstract form, aside from maybe pseudocode. So these agents, lambda, are intended to be the abstraction over something like Q-learning with maybe a special class, big lambda, of like the Markov policies. But yeah, it's a great question. It's one maybe we can come back to throughout the talk, because the other piece I'll emphasize is that we'll need to talk about big lambda and other variations on it. And so we also needed a symbol that would stand in for like big pi effectively. But yeah, thanks for the question though. Any other questions here so far? Okay, great. So I think in the interest of time, I might, let me just briefly say, we'll occasionally talk about HH prime as a history concatenation. So this is just smushing two histories together. I'm gonna skip through some of these other details. Rewards are there. They're going to be these functions depend on history. This will bring us to, this is a proposed definition of the RL problem, which is given a set of agents lambda, we'd like to find the agent that maximizes performance in that environment. So we think of this as the RL problem facing us as the agent designers rather than the problem facing the agent itself. So this is our treatment of kind of standard RL. So next, what we'll do is come back to this, this main idea I mentioned before, this distinction between agents that solve problems and then agents that search forever. And we'll now use this new language we've introduced to try to make this distinction more formal. Okay, so the main idea of the work is that we can really distill two main facts about agents, and then everything flows from these two facts. The first is that every one of these agents can be understood as searching over a set of behaviors or a set of policies. The second main fact is that because all of these agents can be thought about as searching, we can just ask, does that search process eventually end, or does it continue forever? And we'll just make these two facts a little bit more precise, and then that will allow us to define continual RL as the setting in which all of the best agents are those that keep searching forever. And so when I mentioned this sort of agent emphasis, we're going to fill in at least one proposal for a model of agents and agent families and agent classes. So one way to think about this notion of the search process is we're going to start from what we'll call an agent basis, which are basically these sort of atomic behaviors in some ways. It's like a policy class that we think of as an agent as being able to represent. So maybe with Q-learning, it's the set of greedy policies over a set of Q functions. So here I've represented them as these three shapes. And then we can contrast an agent that converges, which is one that keeps switching between these elements, and then eventually just adopts one fixed element, say green circle, with an agent that learns forever as one that will keep switching indefinitely between these base behaviors. So maybe if we were to place this with a K-armed bandit, excuse me, we can think about a convergent agent as one that eventually just pulls the same arm indefinitely, with a continual learning agent that will keep switching between which arm it's pulling. Okay, so how do we make these two notions more precise? The first fact that we can understand every agent as searching over some base agents, we'll introduce with this thing we call the generates operator. And the second, we'll introduce what we call the reaches operator. So these are two operators over agents that make this notion of the search process more precise. Okay, so the generates operator, the main idea is that every agent that we write down can be understood as a pair comprised of a policy set and then a learning rule that switches between that policy set. So this policy set we'll call an agent basis. And this agent basis, which is this, again, this kind of atomic set of behaviors, will generate what we call an agent space, which is big lambda, which is all of the agents that switch between the elements of that basis. Okay. So I'll define each of these components in a little bit more detail. But I would say this is the main idea of the work. And once we get this piece on the table, it unlocks a lot of other perspectives. So we'll first define an agent basis, lambda b, as just any non-empty subset of the space of all agents. So it's just, we can think about this as a policy class. So if once you write down, say, a neural net for representing your policy, so maybe the actor and the actor critic, it's all of the assignments of the weights to that actor network. That would be the basis. And then any element of the basis is a particular assignment of weights. It's a particular policy. And then with that basis, we then ask, how does an agent switch between the elements of that basis? So it maybe chooses to play, say, the green circle first, then the blue triangle, depending on what experience happens. And that's how you generate this space of possible agents. So lambda 1 starts time by playing the policy represented by blue triangle. And then depending on what happens next, it's going to choose a different policy. So the mechanism that's doing this choosing, we call a learning rule. So it's a function defined over an agent basis, lambda b. So it's this little function sigma that maps any body of experience h to a basis element, lambda b. And again, we'll adopt the same notation. The blackboard sigma is the set of all learning rules over this basis. And then big sigma is just any non-empty set of learning rules. Okay, so here next we'll get to one slide that we'll need to stare at for a little bit, which is the articulation of this idea that we've mentioned on the previous slides. So we say a basis lambda b will generate lambda, which we denote with this little turnstile, if for every agent in the set, there is a learning rule such that that agent can be understood as playing that policy, that basis element lambda b, at that history. So this is what we mean by generates. Every agent in the set, for every history, you can find a learning rule that plays what that agent does at that history. So in other words, the learning rule switching between elements of the basis defines the agent. It's just a recipe for looking at what the agent could be doing under the hood. So maybe as an example, if we think about a basis as generating the singleton set, it produces a single agent. What that can mean is for this history, if we look at each sub-history, so maybe this first experience, there has to be one element in the basis that produces the same action distribution as this agent. So we require that this equality holds in this blue box, that what the agent does is equivalent to what the learning rule's basis element lambda b plays at that history. Let's say that's this blue triangle. And then after this additional experience, A102, maybe the learning rule switches to the green circle. And these two, again, have to be equivalent. So that's the intuition of this notion of generates. We use the term basis as a sort of reference to like a basis vectors kind of spanning a linear space. This is intentional because we tend to think about this in kind of as like a metaphor for that kind of concept, where we start with some set of sort of atomic behaviors that create a set of agents that can all be understood as switching between elements of the basis. Okay, so that is probably the densest part of the talk. So I'll just pause to see if there's any questions. How are we doing? Yeah, question, please.
Sure, I'll go ahead. Does the basis stay fixed over time? Like, yeah, I'm just trying to understand that.
Very good question. We tend to think about it as fixed. So
okay.
Any time where maybe the basis would grow, we might just start with that the basis that's already grown from the start of time. And maybe one way I've like thinking about this over time, like after we've written the paper, is that the basis is it's kind of given to us as agent designers as the set of possible policies that we can write down. So again, if we started with a neural net, say if we're using maybe DQN, that architecture that we've chosen to represent our policies or our Q values, that is the set that defined by the basis. And then when we assign weights, specific weights to that neural net, that's elements of the basis, where then our learning rule is the thing that's updating those weights. So picking the next policy to play in light of experience.
Okay, I understand. But I guess in that sense, and maybe at certain time steps and depending on the learning rule, there's elements of the basis that are like unreachable or like that.
Absolutely.
Okay.
Yeah, so some learning rules will, and in fact, I find the kind of structure on the basis induced by the learning rule is pretty interesting, maybe in its own right, where some learning rules, all the basis elements will be reachable at all times, whereas other learning rules maybe are, induce like a star graph over the basis where they eventually only settle on these sort of fixed points or something like
that. Okay, cool. Makes sense. We have another hand up. Sam.
Hey, David.
Hey, Singh.
Yeah, so I have a question on this this framework. It seems it almost opens up a sort of a way to study learning rules and their effect on agents as sort of dynamical systems, as the information, so the data that collected by the agent will inform, like, will be used by the learning rule to update the weights of the agent. And seems it opens up a lot of things on being able to treat these as in almost in a control system kind of way.
Mm.
Do you have any comments or thoughts about that?
Yeah, definitely. It's a really nice point. And I'd say one of the things I'm quite excited about these kinds of directions that can make use of this abstraction over agents to start to study maybe new aspects of an agent's learning process. Like you said, maybe treating it as a dynamical system. I hadn't thought about that particular direction, but I would love to chat more about that. I can comment on maybe one thing we did play with a little bit, which was to think about different families of learning rules and what might separate them. So I think at lunch the other day, some of us talked about model-based versus model-free algorithms. And one thing we tried to do was to capture what is a model-based learning rule as opposed to a model-free learning rule. Is there some way we can kind of fundamentally divide between these two things? And then can we study the consequences of maybe those two families? So just very early thoughts, but yeah, great, really nice suggestion, and I'd love to talk more on these directions.
Yeah, sure. I don't want to take too much of the presentation away, but I read some stuff in the supervised learning area where like they study information flow through during learning, and it seems there is like a connection or like something relevant there, but where like the continual RL problem and the RL problem is even more interesting because you have this fact that the agent controls the future trained data. So the future information that will flow through the model. So it's
Nice.
a feedback loop, right?
Yeah, interesting.
Yeah.
Oh, that's quite nice.
Yeah.
Very cool. Yeah, thanks, Sam. Let's chat more offline for sure. That sounds great. Excellent. Okay, so I'll just quickly highlight one result that comes from this generates operator, which has a few parts. So the first is sort of the main, this main fact that I've highlighted along the way, which is to say, if you take any agent environment pair, you can think about that agent as though it were this learning rule searching over this basis. So that's really the main takeaway here. The second part of this theorem is that there are actually infinitely many choices of a basis and learning rule pair, such that those pairs will capture what this agent's doing. And there's a lot to say about this, the fact that there are so many, well, infinitely many such choices. And André on the project really liked this phrase of, learning is in the eyes of the beholder. It sort of suggests that when we choose a basis in a learning rule, it's like adopting a reference frame on how to understand what the agent's doing. And once you pick a basis in a learning rule, it's committing to a frame of reference for thinking about what the agent's doing. It's like, well, the agent's has this policy class and it's searching over it in this way. But what this theorem tells us is there will always be other ways to look at what an agent's doing. So this is, I would say, one of the main results from the work. But the real big takeaway is that every agent, so this history-based function lambda, can be equivalently understood as a choice lambda b and sigma. That's like the main point. And I think as I've been exploring some follow-up directions, it really all boils down to taking advantage of this fact. It's just a way to look at what an agent's doing. Okay, so the next operator is a bit simpler. Now that we have this search process established, it says that an agent will reach a basis when it stops its search. So we had this notion of an agent basis, these three behaviors. An agent that reaches the basis will just stop switching eventually. So it will settle on, say, these green circles. So again, we need this kind of complex logical statement with some quantifiers. But the core of this is to say an agent will squiggly arrow lambda b, which means it sometimes reaches the basis if on some history that can occur in the environment, the agent will stop its search, which means it becomes equivalent to one of the base behaviors. So this is Q-learning, eventually setting its step size parameter to 0 and just playing the same policy forever. It will reach the Markov policy basis. So what this operator gives us is a way to subdivide the set of agents lambda into these different components. So we have the lambda b, the basis, as a subset here. And then we have 3 different modalities of reaches. So the one we introduced before with sometimes reaches in the top, which means that that agent will sometimes kind of converge or reach this basis. In the box, we have the agents that will always reach the basis. So regardless of how history plays out, the environment and the agent kind of force it to be the case that the agent will pick one element from this basis and play that element indefinitely. Or on the bottom, the agents that never reach the basis. So this is the agents that always keep switching their basis element regardless of what happens. So one way to write that down is if we think about a basis again as these 3 circles, we can enumerate all the histories, and then we can just ask, across all these histories, is there at least one where the agent stops switching? Does the agent across all of them never stop switching, or does the agent always stop switching? And that's what gives rise to these notions of sometimes, never, and always reaches. We summarize this fact with the following little remark that just says that sometimes reaches and never reaches are strict negations of each other. So one of them has to hold. So said differently, every agent will either fall into one of 2 camps. It will eventually stop its search, or it will search forever. And so that was our goal from the beginning, was to be able to precisely state that kind of distinction, which we believe we're getting close to having done now with this new piece of language. Okay, so just to summarize, we start with a basis and we say we generate an agent space lambda using that basis. So that's all of the agents that can be understood as searching over that basis. And then the reaches operator describes this distinction of what happens in the limit with the agent's search. Does it eventually stop, or does it keep searching forever? Okay, that's maybe a place to pause and just make sure folks are content. Yeah, any questions here? Yeah, Samuel, please.
Yeah, so I was wondering as well when I was reading the paper, what would you characterize if you're reaching like a sort of equilibrium between switching endlessly between 2 policies in a cycle? Would it be still a generate or a reaches?
Yeah, good question. So according to the way we define things, an agent that switches repeatedly back and forth between, say, one basis element and another, by our language, that will still not reach the basis because it's still switching. However, if you did this sort of change of basis where you combined that switch into a single agent, then it would reach the basis that kind of embeds that switching into the basis itself. So this is just reinforcing this notion that there are multiple reference frames we can adopt, and it just depends on which reference frame you choose.
Oh, hence the learning is in the eye of the beholder.
Yeah.
Maybe it's not actually learning, or like most people would not consider it learning if like it's switching endlessly between 2 policies, kind of like the static problem, right? But it's you're saying that basically it's like a choice of basis changing the basis can remove that.
Exactly. Yeah, that's exactly right. So the commitment to the basis is kind of fixing your reference frame in a way that you're committing to what changes in behavior count as meaningful. And so if by picking this particular basis, we say any change in basis element will be a meaningful change in behavior, and we'll call that learning. So switching back and forth as a consequence is still learning on that view. Yeah.
Okay. Cheers.
But yeah, lots of subtleties here for sure. Yeah, great question though. Thanks, Sam. Okay, so with these pieces, we're now in a position to define continual RL. We start by defining an agent as a continual learning agent. This is all relative to lambda b, so this is from our reference frame. So this is saying an agent is a continual learning agent if it never reaches its basis. So this is one that keeps searching forever. It keeps switching between its basis elements. If the basis is infinite, it might never cycle, it might never repeat. But if the basis is finite, then it will cycle, and it's just a matter of this notion that changes within a finite basis still count as learning. This gives us a notion of a convergent agent as well, which is one that just always reaches the basis. So that means no matter how the interaction plays out, the agent will always eventually decide to settle on one choice of these policies. Let's see, I think in the interest of, okay, I'll briefly mention this slide. So we talked about how this basis on the left is generating this one on the right. I'll just highlight that every generated agent space is subdivided into these 3 different agent sets. There's a continual learner, which is the ones in green, never reach their basis. They continue searching forever. And then there's the convergent agents on the right that sometimes reach the basis. You could go stronger and require the always reaches, which is a strict negation of these continual learners. But anyway, this is a way of just saying, given an agent space, some of those agents will converge, some of those agents will be continual learners. And so with that, we propose the following definition of continual RL. And there's a lot of details here, but the main idea is that all of the optimal agents lambda star, which are just determined by argmaxing over this performance V, we require that all of those optimal elements are continual learners, so they never converge in this environment. So it's maybe one thing to emphasize here is that we are in fact talking about an RL problem. So the object we're given is an environment E, a choice of performance V, and then an agent set lambda. So we believe that those are the ingredients needed to talk about an RL problem. And we suppose that we have a basis that generates that agent space. So it's we're adopting a reference frame for understanding that agent space. And in fact, the way I've started to like framing this more, we didn't actually put this in the paper, is to frame it from the perspective of learning rules. So that's to say, if we're given an environment and then a pair of a basis and a set of learning rules, we can think about the set of agents that that basis and learning rule set generate. And then we again just require that it's a CRL problem if all of the optimal agents don't converge. But what this does is just it emphasizes the fact that lambda B and the learning rule set are kind of the levers that we as agent designers have to play with in order to design our agents. Okay, so that's how we tend to think about this definition. The rest is, there's a few examples I can go through. I'll maybe walk through the first example and then maybe we can just go to some questions because yeah, just in the interest of time. Let's see, so the example is intended to just be illustrative. It emphasizes some non-stationarity, but I may be a little bit reluctant to say that the non-stationarity is kind of the main concept at play, even though it is quite important. I think there's, continual learning and non-stationarity have a deep connection with one another. So we basically just want to show that this kind of traditional notion of multitask learning in RL is accommodated by this view. So this notion of having a distribution over, say, MDPs, where the environment occasionally resamples a new MDP, can be well thought of in terms of this framing of the CRL problem. So we said there are 4 components to the CRL problem. There's E, the environment. So here we'll define the environment as just a collection of MDPs. So we could think about this as, say, n little grid worlds, each with a different, say, transition structure, different walls, rewards, this kind of thing. We'll assume that they have what we call a shared environment state. So these are the observations. They're all just XY coordinates. And we'll assume that there's some constant probability of switching between these different MDPs. As I mentioned, that environment state is just the observation. And then the agent is only going to be able to see its XY coordinate, but not the underlying MDP's kind of identity. So it just knows XY, and it has to learn what is going on in, say, M2, given what rewards it observes and what transitions it observes. In terms of performance, we'll just adopt the average reward. So Ben and some of his students have they put out this really nice paper on, they call it Continual Learning as Computationally Constrained RL. And they have some really nice justifications for adopting average reward in there. We just choose this in this example for illustrative purpose, but there's kind of more interesting philosophical stuff to discuss there. The agent sets we'll just say is the set of Q-learning implementations. So you can pick what your initial Q function is, and you can pick the step size parameter alpha, as well as the epsilon used in exploration. And then maybe there's an annealing schedule that you can adjust as well. The basis is going to be the Markov policies. So these are the greedy functions of the Q table stored by each Q-learning algorithm. So those are the 4 components. Unsurprisingly, we've kind of set this up to favor algorithms that never stop switching. But we look at a Q-learning algorithm that anneals its step size parameter, so eventually sets it to 0, and contrast that with a Q-learning algorithm that just picks a constant step size. So it's continuing to update its Q function. And because the environment keeps switching between these different MDPs, of course, we find that the one that chooses not to anneal its step size parameter will achieve a higher average reward. The second example is adopted from this really nice survey on continual supervised learning from Mai et al. Again, in the interest of time, I think I'll probably just hop ahead a little bit. There's a bunch of stuff about some more analysis in the paper. I'll just highlight, just coming back to one of the questions that was mentioned earlier before I wrap up. We've looked a little bit about ways of thinking about these learning rules as kind of interesting objects in their own right. So I mentioned we can define one of the core objects is this learning rule. That's how does the agent actually switch between the basis? And we can think about this as a way of capturing something like a model-based learning rule. Or say the learning rule can be written down in terms of an argmax over some environment model E hat. So it's one of the kinds of directions I've been interested in. There's another way to capture some notion of, say, bounded agents. So we can write down a learning rule in terms of 5 different kinds of approximations. So say you have bounded memory, an imperfect model, bounded depth compute, these sorts of things. I think there's a lot to do here to better capture bounded agents. Lots of open questions here. And I think in the interest of time, I would love to hear your questions and thoughts. Maybe I'll just hop ahead to the conclusion. Let's see. So here's the paper. We'd love to feel free to check it out and love to hear your thoughts. Big thanks to, this was just, tons and tons of discussions with lots of people involved in this project. So huge thanks to everyone involved in those conversations. And with that, I'll just conclude and we can go to any questions or thoughts you all have. Thank you so much.